Okay, awesome. So yeah, welcome everyone once again for the office hours in the EPF cohort 4. It's one of our last office hours with guests with AMAs. There'll be maybe one more after this, but for a couple of last ones, we have more special guests, and today our invitation was accepted by Kev. Thanks so much for joining us today. Of course, it's an honor. Kev, you might be familiar with his work. He's now the leader of the ZK EVM research team in Ethereum Foundation. But we would like to get to know you, Kev. What is your background, and learn some context about you before we jump into the present. And if you don't mind sharing some of your journey, how you started with Ethereum protocol, what brought you to the ecosystem, to the core work, and yeah, what were your first contributions?
Thanks for having me on as well. It's great to meet all of you, and it's great to see you again, Mario. Where did I start? It's probably been about 5 years since I joined the Ethereum ish community. Probably about 8 years since being in the blockchain space or around there. I started off by just maintaining a Go version of a non-Ethereum client, just designing a more modular version in Go. Then I moved on to more privacy-related topics, maintaining a privacy client. And from there, just naturally, if you're doing anything privacy related, you sort of move into cryptography just because in order to enable these privacy features that people want, you usually need some sort of cryptography. So my journey started moving more into basically cryptographic or cryptography related problems. I participated in sort of the Monero community for a while I was moving into cryptography related things. And then from cryptography, we sort of needed this thing called a snark, which basically gives you proofs of executions of essentially any function. And one problem that I encountered while trying to learn these snarks and use them for our use case was that actually writing them was pretty error prone. So one thing that I started working on was this programming language called Noir, which allows you to write your programs in a type safe or nicer language, and it will compile down to a proof. It's essentially a proof of execution using the snark technology. And while I was doing this, I think I met up with another researcher called Dankrat Feist, possibly around 2020, so 5 years ago. He told me about an interesting problem to do with this thing called Verkle or Verkle trees. And I was pretty interested in sort of like the cryptography related there and the optimizations that were needed. And that was when I started sort of working on the Ethereum protocol a bit more. It's been about 5 years, and I think it was only last year or maybe 2 years ago where I started doing more Ethereum related things. So, for example, I participated in the trusted setup and the 4844 related work. I don't really remember how I got into it. I think possibly Dankrat just said again, this looks pretty hard, and it looked like an interesting problem. And as of last year, I officially, I guess, joined the Ethereum Foundation full time and started working on the ZK EVM related work.
Awesome. Okay, yeah, thank you so much for sharing all of that, Kev. Yeah, it's very interesting. It's very cool background. We had Tony recently as well, and I feel like similar patterns also based on the privacy Monero, and that's really based and also, I mean, you've been I'm not so you mentioned the privacy tech, and so I'm curious, like, what do you work on these days? How do you see your experience reflecting there? Like, I know that you've been contributing or building the Noir language, for example. That's really cool. And what lessons like this ZK privacy realm gave you that you now apply in the Ethereum in ZK VM? Yeah, what is it like working on the research today?
Mhm. Um, yeah, I guess it's a bit of a misnomer that it's called ZKVM, unfortunately, but yeah, we're here and we can't change it. I definitely say the one lesson I've learned from all of the privacy related things is to try to keep it as simple as possible. Um, Once you try to do anything privacy related, because all of the proofs are created on like the client side or by the user, you need very good performance, and very good performance means cutting edge cryptography. But over the years, I've introduced quite a lot of bugs and found quite a lot of bugs just due to this performance threshold that we need to meet. So with the ZKVM related work that I'm working on now, one thing that I'm really over indexing on is how do we make this as simple as possible. Performance is great, but I think a bug is just catastrophic. I mean, even in the privacy sort of domain, it's even worse because you could have a bug and no one even knows that there's a bug there. Someone could essentially just take out a salary from like the money that's being deposited, and you wouldn't know because well, this is one of the features of it being privacy related. So yeah, I definitely say trying to make things as simple as possible is the biggest takeaway that I've gotten from working on privacy tech for a while.
Yeah, that's a great lesson. Thank you so much, Kev. Awesome. Very well. Yeah, and so another question about the present is like, how do you? So now you are a leader of the team. So I'm wondering like how
Mm.
your responsibilities change, and also like with the recent maybe more focus towards the lean future and uh, yeah, different approach to like the more intuitive future. Like, how do you see the future? What are you building towards? What is it like today leading a team and trying to figure this out? Yeah.
Mhm. Yeah, I guess leading a team is not completely new. In my previous experiences, I think I've mainly only led teams, just a virtue of being super early and or just being there long enough to know like how the tech works. So definitely leading a team is not super new. I think leading a team in the Ethereum Foundation is definitely a bit different than um, sort of at a regular startup, just because the stakeholders in for Ethereum are usually pretty external and pretty vocal about what they want. So you can't just sort of make a unanimous decision as you can with a startup or when you're leading a team. So I say, yeah, that's definitely a new thing that takes a bit of time to get used to, I think, and navigate. With respects to the lean stuff, yeah, I always try to keep an open mind about how things are going. Lean is a very big vision. I think the lean EL is where the ZKVM stuff fits in. And there's also lean CL and there's lean data. I would, yeah, I don't think I formed a full opinion on all of the lean related things. And this is not sort of a property of lean. It's more of when things are too far out. I usually don't try to form too much of an opinion on it. I have like directions that I think we should follow, but in general, forming opinions on things that are too far out, I usually get them wrong. So yeah.
Awesome. Yeah, that's an interesting insight. Yeah, yeah. Maybe it's hard being opinionated in this environment. To be fair, there is especially the research. Yeah, thanks so much, Kev. Yeah, so I mean, we always start with this little fireside chat, but I want to invite everyone to give us a question to ask Kev anything about his work, about his past, present, or future. I believe there are some fellows who are working on related things that are familiar with your work. So please raise your hand and also take the opportunity to ask some questions. So it's not just me here. We get 19 people here today. So hope we get some questions of you guys. Anyone? Okay, Shane. Yeah, go ahead.
Hey, Kev, I think on Twitter you at one point put out a post on how like the minimum hardware requirements to run in Ethereum node are. I'm curious how you think that could potentially change with ZK.
Uh, yeah, that's a good question. So just as a reference, the minimum hardware requirements or the hardware requirement EIP, which I believe is like 7870, defined three different nodes. So one being a full node, one being a validator, and then the validator node was sort of split up into like local block builder or block builder. Um, Once we introduce ZK, so first of all, we add this new type of node called a prover. Technically, you could put them under the builder because if you build a block, in order for it to be accepted, you need the proofs to be attached. So we may not need to introduce another entity, but if we do, then the entity will need a lot more powerful hardware requirements because creating a proof within like 10 seconds or whatever, you need at least GPUs. I can't say the exact number, but it's going to be somewhere in the range of 16, maybe 32 for one proof. And because we need this notion of like prover diversity, because you can't just have one proof. What if that ZKVM is like buggy? They're all sort of complex. So what happens is that you have multiple proofs, just like how you have multiple clients. So the prover, basically the 32 number that I said for 32 GPUs, you need to multiply that by whatever the redundancy factor you need is. It's unclear what this 32 number is or what the number is. So this entity will definitely need to be a lot more sophisticated or at least a lot more powerful. On the other hand, the validator that I don't have the EIP up, but the validator requirements drop significantly because in order to execute a block, in order to validate a block instead of executing or re-executing, you just download a proof, and downloading a proof is about 40 to 100 milliseconds. The good thing about this as well is that it smooths out the worst cases. Like if a validator currently receives a block that's really hard to execute, they're going to need more powerful hardware, or at least it's going to take a longer time to execute. But verifying the proof is sort of constant, regardless of how hard the block is. The asymmetry, as I sort of previously noted, is in the prover. The prover will need to do more work. So yeah, this is how the hardware requirements will roughly change in terms of what the current landscape looks like. The proofs themselves are a bit, at least the numbers we're looking at right now, the proofs are a bit heavier in that we're looking at numbers in terms of like 300 kilobytes, which is a lot, but I think we can do this other technique. I believe POTUS has a EIP or ETH research post on RLNC on how to sort of have a more efficient way of transferring data over the P2P layer, even if the data is actually big, by essentially chunking the data up. Does that answer your question, Shane?
Yeah,
Or
and I was also curious if if you guys are looking at how as the prover, then would that work with 6 second slots if you have less time to actually produce that?
Mhm.
Uh, it seems like from the validation perspective, you'll need way less time, I guess, for the prover to be able to get it out within like a couple seconds or something.
Right, exactly. So with the 6 second slots, I believe there's this an implicit assumption that if you lower the slots time, you also need to lower the gas limit as well. Um, so the prover should be doing less work, but saying that, there is an inherent overhead to creating a proof. So even an empty block is not going to take you 0 seconds. Um, I can't remember what the number is from the top of my head. It might be one, if I remember correctly. But yeah, once you decrease the slot time, you will need to decrease the gas limit as well. Which yeah.
Gotcha, gotcha.
Okay, thank you. Yeah, I think it's very interesting trade-off that we are doing in this future. Where like right now, the if you zoom out, like the requirements for the verifier and like the builder and the validating node are almost the same, right? If you zoom out, with this, it's so diametrically different. It's super easy to verify, but hard to prove, right? So it's an interesting trade-off there. But I'm also so what I'm curious about actually when you mentioned the EIP for the hardware, just a quick question related to that about the hardware recommendations. Do you think it should update with the PeerDAS now with supernodes? Because when I last time talked to PandaOps, they said like it should be similar ballpark, but now that I saw some latest reports from the DevNets, I'm not so sure about that. Like, what do you think? Have you been following that as well?
Um, sorry. Yeah, I think it should probably include supernodes. Um, I believe to become a supernode, you needed to be staking 4,096 ETH,
Yeah.
which means that yeah, your bandwidth requirements will go up, just because you're with 4,096 ETH, you're custodying or you're in charge of more data. It's not just the original data in PeerDAS. There's this sort of technique where you have your original blob data and then you sort of double it for redundancy. And the supernode is sort of in charge of all of this, the data plus the doubling or the extended data. So there is a doubling of the bandwidth required, at least for upload, because when I say that you're custodying or in charge of the data, this means that you're also in charge of like sending it out to peers that require this data as well. So yeah, I think the requirements should somehow put this into, or the hardware EIP should somehow like include this.
Yeah, cool. It was just a thought about the EAP because even like the local block builder, there has like high RAM and space requirements or like bandwidth.
Mhm.
Uh,
Mhm.
Technically, it could fit even the supernode. But I'm just doing a filler here, waiting for more hands to raise and ask a question.
Mhm.
So, guys, please, yeah, use the opportunity. Don't let me take space. I think Dimitris was first.
Yeah, hi. I have a few
Mhm.
questions like related to the previous question, like these estimates that you gave about like producing a proof, um, where it did you take into account like the current status of like ZK proofs, or like are we talking about 16 to 32 GPUs in like 5 years from now, where everything is made much faster and all that? Like, are you taking optimizations on the ZK proofs into account to make this estimate? And the second question that I have is that you mentioned Noir at some point, and I was just wondering, I mean, what are the current tools that we can use in order to minimize bugs in writing code for ZK proofs?
Mhm. Yeah, so I'll take your first question. The 16 to 32, this is, I would take it as a realistic aspirational goal is the best way to put it. I say that just because I haven't actually benchmarked it myself. I mean, I've seen ZKVM teams or newer ones coming out with these numbers, but the numbers that we have personally benchmarked haven't been, I think they're around the 32 to 48 number. This what we're actually proving is a ref. It's a program in ref called ref stateless. So if you look at the ref upstream branch, it's called ref stateless with one modification to the MPT part for the state proof. Some of the ZKVM teams have this new optimization called subblocks. I don't know if you want me to get into the details of that, but essentially it's not been upstreamed, so I'm not taking it as a given for the optimization. But subblocks are similar in spirit to BALs, essentially. But as I said, I haven't benchmarked this, so I don't want to um, say like guesstimate any numbers there because I don't know what's going to come out of it. On your second question, yeah, writing ZK proofs about bugs is pretty hard. I think one direction that the EF is mostly interested in is formal verification. I don't know enough about it to say whether it will stop most bugs. The bugs that I've seen that formal verification haven't stopped have been related to the formal verification specs explicitly excluding that part of the code or something along these lines. So I'd say, yeah, formal verification probably is our best bet moving forward. The issue, yeah, I guess one issue with like one thing you can't do is that like circuit diversity, because if the circuit is different, you get a different proving and verification key. So you're technically proving and verifying something different. So you can't like do the same thing that we do with like client diversity, unfortunately. So it's likely that like fuzzing and formal verification are the best tools that we can utilize. Demetrius, does that answer your question?
Yeah. Thank you.
Thank you.
If you just, on the first question, if you just can provide the references that you mentioned about what exactly are you proving and where is this upstream?
Mm-hmm. Yeah, I can definitely provide the links and also like how we're benchmarking and the abstractions we're using.
Yeah, that's great. Thanks.
Awesome. Yeah, thank you, Kev. Lee, go ahead.
Yeah, I was wondering. I was thinking you want to continue the question before, so yeah, I didn't raise a hand. Can you simply send the link to Mario so that he can share it on Discord? Otherwise, I think the chat here has some issues sometimes.
Yeah, we have the Discord channel. I can take you there, Kev, so we can have also feel free to post anything there.
Thanks a lot.
It's in the
And also happy to see you again since many months ago, and you didn't join the RWC, right? So I didn't see you there. By the way, my question is about following the previous question, because formal methods you always need to model the system, and or it's either proof system or the virtual machine system, and this model may have some issues. So that's usually the biggest challenge for the formal methods itself. And also, I want to learn more about your current work, because I know your previous work. So I want to learn, since you moved to the KVM, what are you doing now, and also what's a challenge now?
So I'll address your first point, which is a good point. So with the formal verification methods, one way to think of how it works is that so let's say that you wanted to have some number that said if a car crashed and the person was in there, there's a 33% chance that they would survive. What you wouldn't want to do is test this out in real life, because, well, it's you don't want to be risking people's lives. So what you can do is form a model, some 3D model, and then just simulate it in this 3D model in some sort of software. The issue is that if your 3D model doesn't correctly map over to the real world, you could be proving something that's not actually true. So this is what Lee was saying, in that the model or your formal verification model needs to accurately represent sort of whatever the problem is that you want it to model. And this is not always the case. You could have a model that's just incorrect, and it could be proving stuff that's correct in that model, but it just doesn't represent real life, or it doesn't represent your circuit or whatever. So yeah, this is definitely true. And I don't actually know how the formal verification folks are solving this problem. I wouldn't know enough about it, to be honest.
I don't think they have, actually. It's kind of like a very old fashioned research trick. I see people spend days and days to think about how to model the things, and hopefully it works, something like that.
Right. So that is definitely a problem that I don't know enough about it, but I guess on my end, what I've been working on right now, I usually move quite a lot up this stack. So currently I'm working on a Lighthouse PR, and that gives us a proof of concept for what does the end-to-end system look like. Essentially, we're modifying the Lighthouse client in order to download proofs, and also propagate them. But the important part is that the client can now download proofs. Whenever it gets an execution payload, it will wait for like 5 out of 10 of the possible proofs. And if they all verify to be correct, then the node will say this execution payload is correct. Execution payload is, if you're not familiar with the nomenclature, the execution payload is inside of the beacon block, but sometimes the execution payload can be called the EL block or the execution layer block. This is the execution layer block is basically the block with all of the things that people usually care about. Like when people say stuff like my Solidity contract or smart contracts, all of this data is inside of the execution payload. So this is roughly what we're proving. We're like proving that the state transition of an execution payload is correct, quote unquote. So yeah, I'm working on the CL stuff related to this at the moment, and also just the standards for ZKVM. Just because we have multiple ZKVMs and they've done things in multiple different ways, and we're trying to like standardize sort of the interfaces between like the program that's being proven and like what does the ZKVM offer in terms of API. One issue that we are coming across that's been pretty hard for me to solve, it's like semi-social, I guess, is this concept of a Linux syscall. Essentially, if you want to prove a ref program, a ref is written in Rust, which is a pretty low-level language, which means that it can compile to something that doesn't assume that you have an operating system like Linux or Windows. But for programs like Go or Java or .NET, which Nevermind is written in, or C#, you can't get rid of this assumption, which means that the ZKVM also needs to be aware of this assumption and needs to prove the Linux syscall. There's about 400 to 500 Linux syscalls the last time I checked, or something along it's in the hundreds. So we can't support all of them. And even some of them are pretty complicated, like mmap, which is definitely going to be called somewhere. It's just always going to be there, and probably clone as well. These are pretty complicated functions in order for a ZKVM to prove execution of. So yeah, we're trying to think of how do we solve this problem, essentially, without sacrificing performance? And are there any ways to sort of mitigate it? For example, Gef there's a different compiler that for Gef called Tamago that we're looking into, that essentially allows you to compile Go programs without this operating system assumption. And for C#, you need to modify this thing called libc, because that's usually where all of the syscalls are being called from. So yeah, this is one of the harder problems that we're hoping to solve by the end of the year.
Wow, I didn't think about this issue before. I only think about like the pure like theoretical part of the ZKVM. It looks already pretty complex, and this one is yeah, wow, that's crazy problem.
Yeah, it's a bit hard.
Okay, thanks for sharing that.
Oh yeah, no worries.
Yeah, thank you, guys. That's very interesting. Thank you, Kev. Okay, Iran.
Hi, Cav. Hi, everyone. So I have a question related to the latest research on the ZK in terms of like what's the major topic going on right now? So, for example, what you're currently research on, and also the main blockers. So, what's blocking this research, and why are you like researching specifically this topic? So, what's the main focus right now?
Yeah, so this is kind of a harder question to answer, just because there's a lot of things that are being researched, but I can try to list out the major topics. In terms of on the Ethereum layer, we're still researching the notion of prover centralization. As I noted, I think in the beginning, or I think it was Shane who asked the question on the hardware requirements. The prover now needs to be a pretty heavy machine, and Ethereum usually we do have sort of an assumption on pretty heavy machinery with the builders, but I think this is not a default thing that Ethereum wants to assume, or at least there needs to be a credible fallback, at least for the builders. If the sophisticated builders don't build a block, then the local builders will just build the block. It just won't be as profitable. So we're really trying to figure out a credible story for the provers. If a prover goes offline, then yeah, you have liveness issues. One research area that we're looking into is distributed proving, which is where validators can run this like auxiliary software and they can prove like, let's say, 1/10 of a block, and this will be pretty easy. I mean, you probably still will need a GPU because none of this is like CPU efficient, but you probably will only need one GPU. So if you think of the numbers that I said before, where I said 32 GPUs, then it might be possible for you to have 32 validators with one GPU, and they talk, they sort of communicate together in order to like create the proof. So I think this is one of the main Ethereum-related research positions. There's also the prover incentives sort of research direction being done by Julian. And this is like, how do the provers get paid? Do we just say that the builders just take a bit out of their profit in order to create the proofs because the proofs are cheap enough? I don't have a super strong opinion on this, to be honest. So I'm not super sure. So those are the more social issues. On the zkVM front, we do see that most zkVMs, because we want them to be post-quantum safe or post-quantum resistant, most of them rely on particular assumptions. I believe there's a proximity prize out, but I don't remember the website for it. It would be good if we could prove that this assumption was like correct, or at least disprove it or whatever. I believe it might have been multiple assumptions. I haven't actually read what that is, if I'm honest. So I think those are the two ones that I can think of right now. If you ask me a more targeted question, I could probably think of more research directions. I just can't think of them off the top of my head, sorry.
That's amazing. No, that was exactly the answer I was expecting. Was just curious to see where the ZK research is going, like which directions. Also because like recently, or like maybe not recently, but like a couple months ago, Vitalik was talking about the Verkle trees, so how to develop like the trees, so which type of algorithm to follow. So I thought it was kind of related and was also a super interesting topic. So was researching also on that, and I wanted to know like your take on that.
Right. Yeah. So I guess Verkle trees are related in that. Yeah. So the thing that the zkVMs prove is a stateless program. Because a zkVM, in order for it to prove something like a stateful program, that's actually pretty hard. Because it needs to prove like the database insertions are done correctly, and this is like a very hard thing. So what they do prove is like a stateless program, and the input to the stateless program is a MPT proof plus the block. So the MPT proof is used to basically say that, and a pre-state root, but let's just say the MPT proof is used to show that all of the reads that happened inside of the block are correct. So all of the reads correspond to the pre-state root, and the pre-state root is just a summary of the state or a summary of the database that you can make proofs against. So if we introduce Verkle, this MPT proof part will change into a Verkle proof, and you'll be proving that the reads done in the block are correct according to a Verkle proof instead. In terms of going the Verkle direction, I think it is at odds with this notion of post-quantum safe, just because Verkle uses this curve called Bandersnatch, or well, the most important thing is that it uses an elliptic curve, and those are not post-quantum safe. So there is another EIP called, I think, binary tree or unified binary tree that I can send a link to. And that is post-quantum safe just because it only relies on a hash function, but we also haven't chosen what particular hash function we want to use. We were going to go for a Poseidon-based one, and the rationale was that the lean or the CL will eventually be using Poseidon, so it'd be good to have one hash function on both layers. But from feedback from the L2s and the ZK rollups, I believe they said that actually it's much better to use something like Ketchak or Blake, because then you're not limiting innovation, because this Poseidon hash function is instantiated over some field, and proving systems are also instantiated over some field. So if you want to have efficient Poseidon, you ideally need to be matching the field that the Poseidon is instantiated over. And I guess I think one other feedback was that Ketchak and some certain hash functions, although they used to be really inefficient in the past, they're actually getting pretty efficient. So yeah, my opinion, I guess my opinion is that we should probably move to binary trees sometime in the future, if not to get rid of sort of the edge cases in the MPT and removing the RRP assumption. And I guess it'd be great if we moved to Ketchak/Blake instead of a Poseidon version, because that just forces us to use a specific field. Yeah, does that answer your Verkle related question?
Totally, more than expected. Thank you so much. It was brilliant.
No worries.
Yeah, thank you so much for diving into that, Kev. That was great. Yeah. Yeah. Any more questions, thoughts? Feel free to ask, raise your hands. So yeah. Oh yeah. Awesome. Who was first? Developer Uchi.
Hey guys, hey Kev. My question is related to your recent work with the consensus client and like proofs. So I'd like you to throw more light on what the consensus client would look like when we now move, when we have this switch, much more technically.
Yep. Yeah, so I guess to give a slight overview of the current architecture, there you have to run an Ethereum node, you need a consensus client and a execution layer client. And the consensus client will speak to the execution layer client in, let's say, there are three methods that it will call. The first one is called get payload. And this is if the consensus layer client needs to build a block, it will say, can you give me transactions in order to build, so that, can you give me the execution payload essentially? Because I need to build an EL block. So the EL will basically look inside of its mempool and say, okay, I'm going to put together all these transactions and here's the block. And then the consensus layer proposer will just like take the block, put it inside of the beacon block and then propose it, roughly speaking. There's also a new payload, and this basically, whenever the CL receives a block, it will send the execution payload in the beacon block to the EL in order to validate that it's correct. And then the third method is basically something called fork choice update, which is if the CL needs to do a reorg, it tells the EL and the EL can do a reorg as well. So when we move over to this ZK attester based client, first of all, the get payload method is no longer useful because there is no mempool, like the EL doesn't have any state. So get payload is just like removed. You have to use mev boost, unfortunately. The next one is the new payload. So whenever the CL gets a new beacon block, it takes out the execution payload. Instead of sending that to the EL to validate that the execution payload is correct, it will say, I'm going to listen on my P2P network for 10 proofs or 5 proofs or whatever the threshold is that they've supplied. And once I've received like 5 proofs, I will then say that this execution payload is correct. The fork choice update is no longer needed because there is no EL to reorg, like the EL doesn't have any state. So the main thing that actually changes is this engine new payload method. Yeah, I don't know if you have any extra questions about that.
Yeah, just more like a follow-up. So in other words, it's kind of like the consensus chain, the beacon chain now becomes like the first class chain in this sense. It now holds the true state of all the chains.
Yeah, so if you're attesting this is correct, you no longer need the EL, you just have a CL, like one binary. If you're building a block, you still will need an EL. So if you're like a block builder, you still need to have the EL state. So yeah.
Yeah. So last question: is there any economical model that we have right now? Maybe something rough, more like a reward for validators, attesters, and most importantly, the block readers, the provers in this case.
Right. Yes, I think this was related to a previous question. So the validators, they don't change. The incentives for the validators don't change. It's just the hardware requirements are decreased. The block builders, the current thinking is that the cost of building a proof is going to be low enough that we can just minus it off of the profits that they're going to get from building the block, and they're already incentivized to build to like make sure the block is like valid by including proofs. So this is okay. We do have an EIP called AD25, which is optional execution proofs, which allows us to sort of roll this out and experiment with things. In this model, the block builder has no incentive to create proofs because the block is valid without the proofs because it's optional. And what we're planning to do is that the EF or a couple maybe provers will just run these nodes and just create the proofs sort of altruistically. This is only while they're optional because, yeah, there's no incentives.
Great. Thank you.
Yeah, cool.
Awesome. Yeah, thank you, Kev. Dimitris, yeah, go ahead. We still have time.
Yeah, so I'm just curious. So at the beginning, you mentioned that especially when developing cryptography, we should keep things as simple as possible. And I was wondering, like, how feasible is this in case you have these like distributed provers, where I don't know, you have 10 machines doing proving, maybe with different zkVM each one, and then you also have the networking. How doesn't that complicate things a lot?
Yeah, so it definitely does. And it's still unclear how we're going to make this simple. Technically speaking, usually you already have something like distributed proving already. Like when you create a proof, you can think of it as there's a sequence of bytecodes. It's not really this, but let's just say there's a sequence of bytecodes. The bytecodes get chunked up, let's say after every 10 bytecodes, and that chunk gets sent to a GPU. So there's already this sort of communication or orchestration that needs to happen. The distributed proving essentially just, instead of having it be intra, meaning just the GPUs are just next to each other and you just need them to communicate, you just need like an orchestrator to like send them data. It's sort of over the internet, essentially. So my hope is that it's not super complicated, but I haven't actually implemented it, so I can't say what sort of like how complicated it might get. But I definitely agree that this could increase the complexity. It definitely won't be done over the normal like validator network. It will have to be like a separate network just for like distributing proofs. And as you said, there's also the complexity of that it's not just one proof, which is what the current zkVMs are doing. Like they only care about creating their own proof and chopping it up into like subsections in order to send to different GPUs. We actually need N proofs, which does also increase the complexity. Yeah.
I see. Thanks. And with this like second network that we need to build, will like areas of the planet that have very low bandwidth be affected and maybe get excluded from the network because they cannot do all of these things at once?
Yeah, so this is a possibility. I think it's probably okay because we want this distributed proving or decentralized proving or whatever people call it. Those are two different words. I know people call them the same thing sometimes. We want this as like a fallback strategy. So it possibly won't be the main thing, similar to how currently most blocks are built by using MEV-Boost. But there is sort of a credible fallback strategy in case things don't go to plan. The downside of this is that also the fallback strategy will likely be slower than using the normal strategy. And yeah, I haven't thought enough about what that means in terms of how the network would work and if it's slow approving. We might just have to benchmark how much it costs to do distributed proving and always have that extra bandwidth anyways. So that would lead back to, I think it might have been Shane's question about reducing the slot time. It might be possible to create proofs using a prover network or using a sophisticated prover in 2 seconds. But if distributed proving takes 4 seconds, then we might want to always say, it's going to take 4 seconds.
I understand. Yeah, thanks a lot. And last question, sorry. You also, I looked on your GitHub and you also mentioned that you have an interest in number theory. Do you mean abstractly or just a number theory related to what you do on day-to-day work?
Yeah, I think it's mostly number theory as it relates to cryptography nowadays. But I do have a lot of number theory books that I like to just read and answer the questions, like pretend I'm a university student sometimes.
I see. Okay, thanks.
Yeah, that's awesome. Yeah, thanks, Kev. Yeah, I learned that like reading actual math book if you are not in school makes me want to learn it more than when I was. It's, if you have any good math book recommendations, please also share those. Yeah, for now, Ali has another question. Yeah.
Yes. I also think about the distributed proving before, and I'm wondering, like, communication, the latency of the communication would be a major bottleneck or not? I mean, proof scale and the proof system, we can try to make some like optimization or other ways, but the communication bottleneck in general is something we cannot do much about that, right? And another question is about I noticed you just released the new internship for 2026 summer, and I'm wondering if you have any tips for the application preparation.
Yes, I'll answer the first question. I have been looking into Xisk's model, which essentially trades off communication for more computation. So instead of sending, let's say 1 megabyte of data, you send like, let's say 100 kilobytes of data, but once you send it over, the prover or the person that you send it over to needs to do more work than if you had sent over the full 1 megabyte. So I think that model looks pretty promising. I can't remember how much data it exactly sends with Xisk, but it did seem pretty minimal. So yeah, if we go with this approach, we would probably want to optimize for bandwidth. And it may be that we need 2 GPUs instead of 1 or something along these lines. But yeah, as I said, I haven't looked into this in enough detail to sort of say anything concrete right now. In terms of the internship, yeah, I guess on my part, I am looking more, at least I think I should have applied to it. I'm looking more for general software engineering skills. It's unclear to me, but I can be super convinced that we need to look into anything that's really low level cryptography, like the circuits for the RISC-V ZKVM. It's unclear if we need someone to look into it, but I can definitely be convinced. I would say I would be over indexing on engineering skills. But in general, when it comes to these EPF, sorry, not EPF, I forget what the what the internship program is called for us. But in general, I would say that if someone is good, there's usually something to do.
Okay. Thanks a lot.
Oh, cool. You're welcome.
Yeah, awesome. We get 5 minutes left. If we have any last questions, something cool to finish it with, feel free to raise your hand still. Um, one quick thing maybe I was curious about is the partial proving or a distributed prover, because the last time I saw a discussion about this, like I was told that it's not really possible, like it's just not efficient or so. So I'm curious if you can share also any resources or any current research on that. It would be really cool to just you turn up the GTA and you switch to proving and you can run it from your gaming PC, just like one GPU.
Right.
It would be really nice. I used
Right.
to do that in the proof of work mining, so it would be really nice.
I believe there was an article out there by Geordie on ETH but distributed proving, I can't remember what it was called. There was an ETH post by Geordie from Zisk, but I can't find it at the moment.
It's all right. I will look into it and feel free to share something if you have any resources later. I tagged you in our fellowship channel in the R&D, or I'm sure you're there. So,
yeah, I do look inside of the GitHub channel for the EPF. I think I saw maybe it was Remy. I might be saying your name wrong, Rhyme or Remy. I think I saw some lean related stuff there. It'd be good to know what's happening over there. At least the lean CL side of things.
Yeah, so we have a couple of fellows working on lean related projects. I mean, Rima and Subik are working together. There are contributions to Reem, and some people here working on the ZK provers. So Rima just left. Anyway, if anyone wants to ask something or share their work maybe on some related stuff, last few minutes, so please use it for some last question, folks. We get a bunch of people here.
Hey Kev. Is there a way to simulate distributed proving, maybe to measure network latency or in general to measure the efficacy of distributed proving?
Yeah, I think we can definitely simulate it in the same way that we simulate the networking layer, just by giving the parameters of what is the latency for creating the mini proof or the chunk of the proof and how big the proof is, and then you can put in parameters for upload and download speed, and you should be able to simulate how long does it take to generate and propagate these chunks of proofs. You might need you might need someone that collects all the proofs, or else you sort of get pretty bad asymptotics where you need to send a chunk to everybody. Yeah, I'm not sure. Yeah, so there's multiple models here that you could go with. Probably just using a central person, maybe the proposer, and you send the proposer everything or something like this would work. Yeah.
Okay, cool. Thanks, Rahul. It's great, great to have you here. Okay. If there are no more questions, I will have one last quick one. Kev, if you have any other advice, if you have any last thought you want to share, maybe something that you wish you knew earlier in your Ethereum career, something to share, some advice to share with the fellows.
Yeah, I guess one advice is to maybe just do stuff, and things usually happen. Don't be shy to ask questions, and yeah, try to just do as much as possible.
Yeah, that's awesome. Yeah, and that's solid advice. Thank you so much, Kevin. Yeah, that's great. Definitely, that's what a fellowship is about. Just like to jump into it and worry about doing the work. Yeah, awesome.
Cool.
So yeah, thank you so much, everyone. Thank you so much again, Kev. It was a great AMA. One more office hours done, and maybe one more left. So thank you so much, everyone. Awesome.
Cool. All right. Thanks for having me. See you guys.
Thank you so much.
Thank you.